Okay, so let's work this problem. So we need to compute the displacement and rotation at C. I may put that rotation part off. So let's just see if we can find the vertical displacement at C. So we're going to use virtual work, which means that we need to find moment equations throughout the frame for both the real load system and the virtual load system. So let's see if we do a little planning ahead. So if you can imagine the virtual load system, we'll just have, I'll assume my unit load of 1 here at C acting down. So that's very similar to this 10 kip force. So looking ahead, it looks like I can write a moment equation from A to B, one equation that's continuous, and then I can write a continuous equation from B to C. So 2 equations ought to satisfy my real moment requirement, and those same 2, or similar set of 2, would help me with my virtual. So that's kind of our general plan. And then we'll form the products of the real moment and the virtual moment and integrate and predict the vertical displacement at C. So let's first start with the real system. What are we going to need? We're going to need some reactions, aren't we? So at A we have a fixed connection, so I'll have a force in the Y direction, a force in the X direction, and a moment at A. So I need to find those 3 things first. Also, to help me with that work, I'll go ahead and get a concentrated equivalent force for this distributed load on the side. So it looks like it's half a kip per foot times 20, so that's 10 kips. And it'll happen right in the middle, that's 10 feet. Okay, so let's find these reactions. So first I'll come down here and I will sum moments at A. Make sure I'm in equilibrium. I'll use right-hand rule. With that sign convention, my moment at A is negative. The moment created by the 10 kip force about A is also negative. And the moment arm is 10 feet. And then all the way out here, the moment by the 10 kip force at the end of the cantilever is also negative, 10 kips. And its moment arm is 10. Oh, a lot of 10s here. So it looks like the moment at A is equal to minus 200. And that would be kip feet. Oh, I left off my minus. Now we can sum forces. So I'll sum forces in the Y direction. I'll assume up is positive. So I have AY acting up and 10 kips acting down. So it looks like AY is 10 kips. And then I'll sum forces in the X direction, assuming to the right is positive. Make sure everything's in equilibrium. So I have AX to the right, and I have my concentrated equivalent force of 10 kips also to the right. So it looks like AX is minus 10 kips. So I have all my reactions. Does that look good? All right, let's go to the real system. And we'll start with section AB. So I'm going to cut the structure here and decide whether I want to work the bottom section or the top section. I'm going to choose the bottom section. And I'm going to orient that with some distance Y. Let me transfer all my forces. So in the X direction, I have a 10 kip force. In the Y direction, I have a 10 kip force. And then I have my moment, which is actually in this direction, which is 200 kip feet. I also have a distributed load acting on my beam, where I can get a concentrated equivalent value. What would that be? Well, this is a distance y, and it's 0.5 kips per foot, so this is going to be basically y over 2, right? 0.5 times y?
Yep.
And the distance to the centroid there is also y over 2. And then at the cut, I'm going to assume my positive moment is in this direction. So I'll say this is the moment in AB. Kind of a busy three-body diagram, but I think that's correct. So now I'll just come over here and I will sum moments at the cut. Make sure it's in equilibrium. Let's see what we get. So starting here, I have the moment at the cut is AB, that's positive. My force y over 2 is also positive, and it has a moment arm of y over 2. What else do I have? I have this 10 kip horizontal force, which is creating negative. I'm sorry, I did that wrong. This is positive moment. Positive, positive. The 10 kip is negative, and it has a moment arm of y. The y force creates no moment, and then I have another positive moment for the 200. So it looks like my moment in AB is going to be equal to, let's see, that's going to be minus y squared over 4 plus 10y minus 200. And everybody in there will have the units of kip feet. Let's check it. So when y is equal to 0, I get minus 200, which seems to match here. And that's really all I've got. Yeah?
The moment you found was negatives. So that's why you do it like that, right?
What do you mean the moment I found was
Like
negative? Well, I assumed clockwise moment, and my reaction was negative 200, so I put it in as a counterclockwise. That straightened out the sign.
That's actually positive.
Then I assumed my moment was positive in this direction. And if I do, this is what I get.
What?
Well, the 0.5 is this 1/2 here. So the 1/2 is the height, and then the length is y. So that's the y over 2, and it just, oddly enough, the distance to the center is also y over 2.
Okay. All right.
Okay, so the next one that I'm going to do is I'm going to cut the structure here, and I think it's going to be easier to look at the cantilever side. So I'm going to cut my structure. The only force I have is the 10 kip force, and in this case I'll assume a distance x1 in that direction, and I'll assume here's my positive moment in section BC. You see that one? So now when I sum moments about the cut, make sure it's in equilibrium. This is, with right-hand rule, that's a negative moment, BC, and my 10 kip force is also negative at a distance of x1. So it looks like my moment in BC is equal to minus 10x1, and that will also have the units of kip feet. Now these two things meet somewhere. Well, the moment at BC, if I go all the way to 10, 10, should be the same moment as this one if I go all the way to 20. So we can do a quick check. If I put 10 in here, it looks like I've got minus 100. If I put 20 in there, 20 That's minus 100. And then that's 200. It's minus 100. So it checks. So our moment equations seem to at least be compatible at B. Give the same moment. Okay? So now, let's do the virtual system. Is this helping at all? We had some issues about the moment. So the virtual system now, I'll have to redraw it. So I have a structure that looks like this, and now I'm going to put my unit load here. I'm putting it at C, because that's where the displacement is, deflection at C, and I'm assuming it's going to act down. And that's the only load on this system. But I have to go back now and recalculate all of my reactions. And after I do that, I have to go back through and get moments for this system in AB and BC. So let's start first with the reaction. Say again?
Why don't you put on the virtual system, why aren't you putting the concentrated load again?
I'm putting a concentrated load here because it's the virtual load, and you always put the virtual load
at your point.
At the point you want the displacement in the direction that you're assuming it's moving.
But why not on the other, like the other concentrated load? You just get rid of everything else?
Yep. The virtual system only has one load.
Okay.
A unit load, and again, at the point you want it, C, in the direction I'm assuming. So all these other loads are not in consideration. So we just have to do a little work here first. Shouldn't be too hard. So if I sum the moments at A to find my reactions, I have this moment, which is negative, and I only have the moment due to one thing, this force. So it'd be minus 1 times a moment arm of 10 feet. So it looks like the moment at A is minus 10 feet. Now, why is the moment in feet? Because we're assuming that our unit load is dimensionless. So instead of being kip feet moment, it's nothing feet moment. Right? That's one way to look at it. Next, we'll sum forces in the y direction. So I've got AY acting up, minus 1 down, so it looks like AY is equal to 1. Really no unit. Again, we have no unit on our load. And then the final one, which I think you can probably see, if I sum forces in the x direction, make sure it's in equilibrium. I only have one force, AX. So AX is 0. Okay? So now I just need to go through this part with these reactions. So I'm going to slide this up over here, and let's do our virtual moments. Now, just like before, we have to have our system correspond to the real system. So I cut it like this before. I'm going to have to do that again. And what's changed? Well, I now have a force of 1 acting up, no horizontal force, and I have a moment of, I think the unit I got was minus 10. Oh, yeah. I assume the other direction. Thank you. And then I have my virtual moment in AB. So I will now sum moments again at the cut using my right-hand rule. This moment is positive, the virtual moment AB. And the only thing that creates moment is the moment, which is also positive of 10 feet. So it looks like my virtual moment in AB is simply equal to minus 10. Then the next section, B to C, remember I cut it and looked at the right-hand side. Now I have just my virtual load of 1 here. And I have a distance also predefined of x1. Sorry, let me slide that up a little bit so you guys can see it. And then I have my internal moment from B to C. That's not a difficult moment to write. So I would now sum the moments at this cut and make sure I'm in equilibrium. And what do I have? I have this moment, which is negative. And the 1 is also negative through a distance x1. So it looks like my virtual moment from B to C is negative x1. And that will also just be in feet. So all the hard work is done. Now we just need to put everything together. So now my displacement at C will be the integral. I'll do AB first, so that's going to be from 0 to 20 of the real moment. Here's the real moment. And here's the virtual moment. So I'll start with the real moment. I'll have minus y squared over 4 plus 10y minus 200. Real moment. Virtual moment. Minus 10 dy. Oh, everything needs to be divided by EI. I think I'll just multiply this by EI right now to take care of that. And then I'll add to it the energy from section BC, which in this system starts at the right-hand side and goes to the left. So I'll go from 0 to 10. The real moment was minus 10x1. And the virtual moment was minus x1. And that'll be dx1. So there's my virtual work equation. I don't think that's too hard to do. We might be able to knock that out. Do we have time? Yeah, we have time. All right, let's see what we get. So everything gets multiplied by 10. So what is this going to be? This is going to be negative 10y cubed over 12.
Wait, it's multiplied by negative 10, right?
Correct. I didn't see that other negative. Thank you. And then be minus 100 y squared over 2 plus 2,000 y. Did I get that right? And let's evaluate that from 0 to 20. This last one's a lot easier. That's going to be 10x1 cubed
Squared.
over 3. And that's from 0 to 10. So you guys have to help me out. Somebody evaluate all that. This one I can do. That's 10,000 over 3. Did I get the signs right? Positive, negative, positive. Yeah.
First, go ahead. It's 66,666.7 on the left side. Is that what you got?
66,000? That seems a little high.
It does. Got it.
This is negative, right?
Oh, sorry. I have positive on the plus 100 times 20 squared. That's not wrong. 26,666.7. Negative.
No, it should be positive.
I got the same number.
26,666.7.
Yes, sir.
And this last one is, that's 10,000 divided by 3, so that's 3,333.3. And those should all have the units of kip, feet, cubed.
So it's just 30,000.
Oh, that's convenient. Okay, so then the final displacement, oh, that's not A, displacement will be this divided by EI. So I'll have 30,000 kip feet cubed. Sorry about that. If you go back and look at the original problem, we can see that the value for E is 29,000, and that's kips per inch squared, divided by I, which is 1,000 inches to the fourth, and then you convert it, you get 1728 inches cubed per foot cubed. Looks like you get about 1.6 inches. 1.7 inches. What do you guys get?
1.79.
So 1.79 inches. That seems reasonable.
Isn't that extremely huge or no?
It just depends on the problem. I mean, 20 feet in the air, that's almost 2 stories. And then you cantilever that out and it's unsupported. That's not an that's not an unreasonable result.
I'm thinking about slope rotation.
Okay, so this problem has taken us about 22 minutes to solve. I've taken my time and gone through it and interact with you guys, but really, for you to do on the exam, it's not unreasonable. You just had to find some moments, but what I would probably do on the exam is ask you to just stop right there. So not a harsh problem. I think it's very doable. Any other questions? Okay.